fractal antennas. Normally an antenna has to be cut for the frequencies or frequency that they're being used for. And thus the standard antenna will only work well at that frequency. And making log periodic antenna arrays, around since the 1950s, invented by Isabelle and Duhamel, that are such fractal arrays. They are common form used in TV antennas as the arrow-shaped thing that used to be on your house. And what they would do is they pick ranges of frequencies so that each individual element would work across a certain range, which has a bell curve-ish kind of thing to it, and they'd kind of overlap, and that's how you'd work with them. And they're log periodic, which means they use logarithms to create these individual points. And depending on which ones you switch in and out, you can actually make them do interesting tricks, but mostly they're just hooked up in a certain way. They are a common form used for TV antennas and are arrowhead in shape. But a fractal arrangement of antenna elements, and not recognized initially as having self-similarity in their attribute, fractals, they work well too. A fractal antenna response differs markedly from traditional antenna designs in that it is capable of operating with good to excellent performance at many different frequencies simultaneously, because each element component can bring in the signal. This is the equivalent to setting up multiple antenna arrays and then mixing the signals and getting them pulled in. I don't know if you know this, but cable companies using a wide spectrum and putting it through one cable, that took a lot of work to mix them together. That's a multiplexing thing. Here's how it works. The fractal structure as a virtual combination of capacitors and inductors makes the antenna so that it has many different resonances which can be chosen and adjusted by choosing the proper fractal design in the first place. There's multiple designs. Below you'll find links for log periodic antenna, Benoit Mandelbrot, the fractal antenna, Mandelbrot sets, which are different each time, some YouTube videos on it, and a couple of pictures I might even use. Benoit Mandelbrot Fractals and Antennas, Nathan Kohen cell phone antenna. And now we get to that point. That little square postage stamp antenna most of you don't know is inside of your cell phone. What does it look like? Well, I'm going to do a simple one. I'm going to bring up the dimensions of an antenna. This isn't some spacey symbol. X, Y, Z. You have to get the signal from every angle. If you don't have to, remember your cell phone's at all sorts of angles, but most of you hold it up like this. In order for it to work, you need a wire with the same polarization as the antenna source, right? But what if you do this? X, Y, and Z done as a straight line. And then you do another one where all the wires are the same direction, the opposite direction, and are, if it points up, the other one points down for another phase. Okay, what if you take all three angles, just make a square, and have them all, connected to each other with little mixers? Each one of those little antennas could be configured to pick up a certain frequency range, a really limited one, and mix them together to get the best possible signal. And if you're transmitting, they would all just activate at the same time. Well, they'd have to work with each other. Now it gets all complicated. How do we fix this? Well, it's based on frequency. So we start off with a simple idea. We'll make a clover design, deliberately making it to where it goes, has a Mickey Mouse here, over here, here, and then over here. 3 of them. Not 4, 3. And then within them, we make it have the same modifications to where it looks like 3 little ears on all of them. And those have ever smaller little ears on them. And depending on the size ratio, each layer will cover a short frequency hop instead of doubling, and that sort of thing. And you get it to where each of them has these angles to them, because you're doing all these bends in them, to where they come to a point and kind of stop at a 90-degree angle, or maybe it's a curve, or maybe it's just like that. And that acts as a stopping point to where the signal can resonate through this piece of wire. And then as it gets smaller and smaller, these collectively end up looking like longer antenna leads. in the same surface area. You can drastically reduce down a transmit and receive antenna to that size. The multiplexing is already handled by the circuitry to transmit a signal while you're receiving it through the antenna. You can just have two antennas or just one antenna with two inputs. Because your cloverleaf comes down here, you can send here and receive here, and the signal might not even go back through it. This allows you to get away with that. One of these is also used for making a really simple element bow tie antenna for Wi-Fi. I'll leave links below and videos as well. But the point is, this is an example of somebody doing something that at one time was just considered a scientific curiosity. It's fun looking, to it being converted over to something you probably are all using right now. They're called antennas. Been around for a while. Before that, through the 1950s, we all had that iconic Yagi-like antenna. That's the name everybody gave it, even if that's not necessarily true. Sitting up in the air, pointing somewhere, sometimes pointing away from the source. So I'm going to leave some links below. This is mostly to start a conversation on the subject. It's a nice technical subject. I'll include a graphic for the video, if I have to make it, that shows one of these. And while they are patented, they are based on simple mathematics. The ratios from one stage to the other, that's where things get important, because you want it to be able to cover a wide range of frequencies. That's where it gets difficult. That's when you have to do math. And then you just have to build the thing and see what happens. And I'll try to include a whole bunch of links to cell phone antennas and these fractal antennas. Many people are making them and trying to make them look pretty, and are doing them up, and they do work really well, by the way. But they attribute this to some sort of sacred resonance mathematics ratio thing, which is exactly what the hell's happening. That's why I'm doing the video. Someone asked me, why does this look so pretty? And the thing is, I love it when something has a real scientific basis or mathematical basis, but it's still mind-bogglingly pretty looking. They look like snowflakes, so I'm going to aim you at those images. Thanks for watching. Have a good day, and good luck with that. And you can go ahead and etch an a copper plate to look like one of these. It'll look like an artwork. You can make these. No, they're tutorials. I'm going to link them below. Bye.